Hi everyone, welcome back to the video for calculus and analytical geometry 2. In this video we're going to continue our topic of parametric equation, and now we come to the last topic of parametric equation. We're going to talk about the relationship or what we can do in calculus related to parametric equation. The topic will cover 2 points. The first one is slope and tangent line. So we are going to identify, we are going to determine the slope and tangent line equation of a, a kind of curve, but the curve is given in the form of parametric equation. And the second one, we are going to talk about the area of surface revolution of a curve given in the parametric equation. So let's start. So the first one, we're going to talk about the slope of a tangent line. Slope of tangent line and derivative of parametric equation and how is it related to each other. Now let's recall first how to get slope from a function in the form of rectangular equation. You know that in previous topics of calculus, we learned about derivative. We know that the derivative of a function at a certain point is actually the slope of the tangent line of that curve in that particular point. So when we talk about slope here, we actually we can do it by determining the derivative of a function at certain point. Let's say if we want to point, for example, we x y, so the slope or m is actually f prime x, which actually just the first derivative of the function, and we plug in the x of the point coordinate. So that's what we learned before. But if this is in the form of rectangular equation means like in the form of like y equal blah 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 with, or we can say it's function of x. Okay, we have a variable. So under the same logic, we can determine the slope of tangent line of a curve with the curve is defined by a parametric equation by doing the same thing. So we actually determining the derivative, but we did it with, so the slope will be, sorry, change color. So the slope in parametric equation of tangent line of a curve given in parametric equation is actually just the same. We did dy dx. And what is it? Let's take a look. Here you go. So if we have a smooth curve C and it is given by a parametric equation, as we have talked before, in parametric equation we have x equal a function of t and y is another function of t. So t is, remember, t is the parameter. Okay, then the slope of c at the point xy is dy dx. We use dy over dt or dx over dt when dx dt is not 0. So what is this? So dy dt is actually just the first derivative of x with respect to t. So you find the derivative by t, not by x. And because we know that dy here is a function of t, so y equals something with t, and dx dt is just the same, first derivative of y with respect to t. So it's actually quite simple. What we did is just finding the we just divide the first derivative of x with respect to t divided by the first derivative of y with respect to t. Now let's try an example to so that we can get a clear understanding of this one. Now let's take a look at an example here. So we have a curve. It's called a prolet cycloid. So prolet cycloid is given by the equation x equal to t minus pi sin t and y equal to minus pi cos t. And this cycloid crosses itself at 0.2. Here, this point 0.2. So find the equations of both tangent lines. As you can see here, the curve is like this. You can see that this curve is actually not a curve of a function. If we want to find a tangent line by using the normal derivative, mean the derivatives of a function of x, we have to define first the function based on the rectangular equation. We have to consider the interval, but it is very easy for us to find the derivative using the method of using parametric equation. So as you can see here, we have the curve and there's a point, because the point here is the point of like the intersection of the curve itself. We will find two tangent lines. The first one is going this way. So the first one is, let me change color. The first one is going this way and another one is going that way. Means we are going to have two tangent lines touching the very same point. So what we are going to do is finding, as you know, that the slope will be dy over dx, while we know dy is dy over dt divided by dx over dt. Okay, so we have to determine first the dy over dt. Let's see here, let me use it here. So dy dt is the first derivative of this. Derivative of 2 is 0. Derivative of negative pi cos t, it will be pi sin t, right? And now we find this derivative dx dt will be, derivative of 2t is 2, pi sinus t will be negative pi cos t. There we go. So we have it. Now we plug it in here. Where dy dt is pi sin t over 2 minus pi cos t. Let me write now. So this is what we get for our slope. So the slope of this function, the slope of this curve at that point is actually this very expression. Here you go. However, as you know, because we have two tangent lines, means there will be like two slopes come up from this expression, because this expression like based on the value of t, based on the value of t. So you may realize that we need two value of t. There will be two value of t, two values of t. How do we know? First, as if we did it with rectangular equation, we can just directly plug in the x, right? But now, because we don't have the x, we have the t, because it's based on the value of t, we have to determine the value of t. As you know, the point is actually 0.2, right? So this is actually the value of x, it's the value of y. So considering the equation of x and y, we can actually find the value of t in that particular point. So we actually can, let's say, because as you know the y equation is simpler, let's choose this one. So y equal 2 minus pi cos t. We know the y is 2, so we have 2 minus pi cos t. So it's actually 0 equal negative pi cos t, while cos t means will be 0. So what is the value of t so that the cosinus will be 0? We know that t will be pi over 2, or it's 90 degree, or t will be negative pi over 2, which is 270 degree. Okay, so we already have our value of t, the first t and the second t for here. Okay, so the m will be 2. Let's make this t1 and let's make this t2. So our first m1 will be pi sinus pi over 2 over 2 minus pi cos pi over 2, which actually pi sinus of pi over 2 will be 1. So we have pi times 1 over 2 minus, which cos pi over 2 is 0. We have 0 over here. So we have pi over 2 is our first slope. For the second slope, we have the same thing, pi sinus negative pi over 2 over 2 minus pi cos negative pi over 2, which we have pi times negative 1, and this is the same thing, 2 minus 0. So we have negative pi over 2. Okay, so we already have our slope, but the question asks about the equation, so let's write. So the first equation, we will use the equation y, like the general form of a line, x minus x1. So we have for the first line, we have 1 y minus, our y is actually this one, so it's 2 equal our m, the first one is pi over 2 times x minus 0, because x1 is 0. We have y equal pi over 2x plus 2. So it's the same thing with the second line, but with different slope. So we have y minus 2 equal 9 pi over 2x minus 0. So we have y equal negative pi over 2x plus 2. So here you go. We have our two equations of tangent line. Okay, as you can see, the slope is, the first one is positive. It's this line, because the line is going that way, and the second one is this is going this way. The second application of the parametric equation is also to find area of the surface of revolution. This is the same thing that we learned in the rectangular equation, but now let's see what is different from the area of surface of revolution of a curve given defined by a parametric equation. If we have a smooth curve C given by a parametric equation x equal ft and y equal gt, and it doesn't cross itself on an interval a to b, so this is the interval of t, then the area S of the surface of revolution formed by revolving C about the coordinate axis is given by the following. So the first one, as you can see, the first one is if we revolve revolve the curve about the x-axis, then we have gt, it's 2 pi times the integral of from a to b of gt times the square root of this dx dt, like the derivative of the x and the derivative of the y square. Okay, let me get to the okay now. And for if we revolve the curve by y-axis, then we have the y have x over here. If you revolve the curve by x-axis, then you will need a function of y. So you can see that this is, if you by x-axis, then it will, for example, there will be a function like this. It's revolved by x-axis, then you will need the arc here times dy over there. Okay. Well, if you revolve by the y-axis, then you will need x over there, because you will need to revolve y, then you will need, this is the arc, and times the x over there. Okay, there will be the revolution will be something like this, and it will be something like this. Okay, so it's actually the same logic used for the area of surface of revolution when we use rectangular equation or the usual function. Okay, now let's try an example. Let's say C is represented parametrically by this x equal 3 cos t and y equal 3 sin t, with t from 0 to pi over 2. Now find the area of the surface formed by revolving C about the x-axis. So you know that this is the revolution about the x-axis. So we revolve this about the x-axis, so we have our surface area will be as 2 pi times, so we have our boundary here is pi over 3 and 0, and we have, because we are going to revolve about the x-axis, mean we will need the equation of y. So we have 3 sin t times, so we have the dy over dt square plus dx over dt square. Okay, so let's find first our, so dx dt will be, the derivative of this will be negative 3 sin t, and derivative of dy will be 3 cos t, right? So now let's plug in. It's 2 pi integral pi over 3 0 3 sine t square root dy dt is 3 cos t square plus negative 3 sine t square. So we have 2 pi, let me write it below. 2 pi, same thing, 3 sine t, root of we have 9 cos square t plus 9 sine square t, which actually we can find 2 pi integral pi over 3 0 3 sine t times, we know that we can factor out 9, we have cos square t plus sine square t. So if you remember, this one is actually equal 1, right? It's a trigonometric identity. So we will have 2 pi integral pi over 3 0 3 sine t square root of 9, which actually just 3. So we have 2 pi the integral of 9 sine t. I always forget the dt will be dt over here. Don't forget to write the dt, yeah. dt. So we have 18 pi times, so the integral for sine t will be negative cos t pi over 3 0. So we have 18 pi times cos pi over 3 is cos 90 degree, which is half, so we have negative half, and cos 0 is 1, so we have negative 1, so we have plus 1. Okay, so we have 18 pi times half, which is 9 pi. Here you go. So we have 9 pi is the area of the surface.